Okay, so it's my
Okay,
great.
we see your slide. Okay, very good. So, Maxim, you have 30 minutes minus several minutes for questions.
Yes, I know. Okay, thank you very much.
Yeah,
So
I
my
know that you
idea.
know.
Thank you, Victor. Okay, so what I'd like to discuss is the question about possible messengers of new physics. And the main point is that, and I'd like to cover rather briefly some different possibilities which are model dependent, but whose discovery corresponds to what Zildovich used to say: the probability is low, but the expectation value is very high. So I'll cover multi-component dark matter, dark atoms of dark matter, very briefly premodel black holes, which were comprehensively presented before, and some interesting possibilities which arrange us to understand how the standard cosmological paradigm, which assumes that we live in an inflationary universe with baryon synthesis and non-baryonic dark matter and dark energy, just our existence in this universe just is the main messenger of new physics. But the question is, how can we prove this new physics? And the idea is to use what I propose, multi-messenger approach, in which we study additional model-dependent effects of new physics, and they can strongly specify the features of the dark nature of our universe. So there are two principal possibilities to do it. One of them is that if for cosmology, two effects are very important from fundamental microphysics. They are the existence of new conservation laws, which new particles possess, and which makes them stable. It makes them to exist in our universe, so be dark matter candidates. Another thing is that the symmetry of the particle theory can be broken at in high temperature phase transitions, and it can lead to some non-trivial topological defects or structures which appear in the result of existence of some phenomena which are predicted based on the particle physics model. So actually, cosmological dark matter uh, reflects the uh, conservation laws which prohibit dark matter decays. And on that, in that sense, they are something what just prove the existence of dark matter, prove some new conservation laws, so that particle dark matter candidates, they just correspond to the new new symmetries which are leading to new conserved charges, and all the examples of the particle dark matter candidates just demonstrate this possibility. Uh, the most elementary approach is that we have new fluid of gas of primordial particles which were frozen out, and they just now dominate in matter content of the universe. However, it may be noticed that there was some miracle which gives us the possibility to explain the observed dark matter density by freezing out of a few hundred GeV particles, which have cross sections of ordinary weak interaction. However, direct search for WIMPs is very controversial, while the most natural physical model which gave us WIMP candidates like supersymmetry, predicting candidates like neutralina, it should be accompanied by supersymmetric partners at the LHC, and we don't observe them. So it implies much wider list of dark matter candidates, and they are both related to different parts of particle physics problems, because in standard model we have problem of strong CP violation, and there was very comprehensive discussion of the necessity of axion physics in that aspect. In case of supersymmetry, there is a possibility to go far from the energy range of, available for collider, and there may be super heavy particles, in supergravity, there may be super heavy gravitons, which may play the role of dark matter, and it makes astroparticle physics maybe the only way to prove such ideas, as well as cosmological predictions. It should be also noticed that together with this list, which is not complete, we have also a possibility to have model dependent next to lightest particles. If they're sufficiently long living, they can also provide some observable features. So one of the possible questions related with absence of positive results of supersymmetric particle insertions at the TeV scale may reflect, as I already told, super high energy scale for supersymmetry. However, then we have a problem how we can solve without supersymmetry problem of the standard model that Higgs boson has the mass which it has, and so what is the mechanism which provides first of all removes divergence of Higgs boson mass, as well as determines the scale of electroweak symmetry breaking. And composite Higgs boson is one of such possibilities. And in this case, we have a question whether dark matter candidates or constituents are necessarily neutral. Well, they should be neutral, but does it exclude electrically charged stable particles? And here is a very strong constraint on this possibility. And this possibility constraint comes from the fact that we don't observe anomalous isotopes of hydrogen or helium. And these anomalous isotopes exclude existence of stable particles with positive charge. Moreover, they exclude the possibility of stable particles with a negative even charge. Because if you have -1 charge new particle, which is stable, its presence in the universe after Big Bang nuclear synthesis leads to binding of this heavy negatively charged particle with the model helium, and it forms an object which has charge +1, and then together with electron, it gives you anomalous isotope of hydrogen. So actually,
excuse me, Maxim Yurich, can you please close this YouTube window because it blocks the part of the screen?
sorry?
Yeah, this one. Can you please close this window? Yeah.
Okay.
Because,
Sorry. So thank you. The only possibility to solve this problem is to have even charge particle, because if you have particles with even charge, then they are bound with the primordial helium and form neutral atom of what I call O helium if the charge is -2. And if the charge is -2n, they bind with n nuclei of primordial helium. And it gives us the possibility to have some neutral objects which are very non-trivial. So the possible theoretical framework for such model comes from working technicolor model, in which you have techni-quark, techni-baryons, and techni-leptons. Their charge assignment is determined by the cancellation of anomalies. And because it is a cancellation of the anomalies, it gives it doesn't specify the actual value of this charge, and so that there may be stable charged particles, which provided that techni-baryon or techni-lepton charge is conserved, we have a possibility to relate the baryon asymmetry to the excess of corresponding techniparticles, technibaryons, or technileptons. And this excess doesn't depend on the electric charge of these particles. And if they have charge -2, then they bind in some Bohr-like atom, which I call helium, which is very non-trivial because all these candidates are just lepton-like, while its shell is nuclear interacting alpha particle shell. So you have an absolutely different situation when we have in normal atomic physics. In fact, there may be the choice of the parameter which determines the charge assignment of technibaryons and technileptons, and then you have a possibility of such an object which is Thomson-like atom. So you have a heavy heavy particle with -2n charge. It is in the droplet of n helium nuclei, and this nuclear droplet just so behaves like it behaves like a neutral object. And the interesting possibility of this scenario is that you have an explanation why Dama sodium iodine, Dama Libra experiment does observe at high statistical significance some annual modulations which were ascribed to dark matter, while other groups do not observe. The idea is that there are specific interaction of such nuclear interacting object, and its presence in the underground detectors leads its number density within detector follows the flux which comes from the halo, but the effect is not a recoil as normally people assume for dark matter searches, but it is the binding, low energy binding with some nuclei, and sodium can be such a nucleus. And then you have the effect which is observed by Dama. There is also a possibility to, for such, so note that they are, though they have nuclear interaction, they are just collisionless gas in our galaxy. But in central part where the density is larger, it is possible for them to collide, to excite, and the excitation in electron-positron pairs can give a possibility to explain the excess of positronium annihilation line, which was detected by integral. There may be also a possibility to explain the excess of high-energy positrons by decays of some subdominant component in which you have decays of positively charged particles. And this explanation assumes that the mass of these particles, which decay, is less than 1 TeV. And actually, the normal relationship between astrophysical, cosmological, and collider probes for dark matter comes from the idea that in the at collider you have some missing mass or missing energy, but here the approach is to search for multiple charged particles, and in Atlas experiment and in CMS there were constraints which already exclude the possibility for to explain high energy positrons by decays of double charged particles. It doesn't mean that completely all the set of parameters of such multi-charged particle effects are completely excluded. In general, the idea of multi-messenger cosmology is to consider and to compare it with the multi-messenger astronomy, so that you have different effects which are related just with presence of the new forms of matter in the universe in different periods. It may influence Big Bang nuclear synthesis. It may influence formation of large-scale structure. It may just contribute to density of modern universe, and it constrains their existence. But if we have some more detailed information about, which is model dependent, about their properties, it may influence the spectrum of thermal radiation background. It may influence light element abundances. It may just lead to some fluxes of gamma. And here the important effect is that you have what I call non-equilibrium particles. And these non-equilibrium particles, they just are something that either is not present in thermal equilibrium in the universe, or some species like antiprotons in baryon asymmetrical universe, which are completely absent in the universe after first microsecond until the secondary antiprotons appear in galaxies. So actually, primordial black holes were just widely discussed before. So just let me only notice that primordial black holes are a very strong indicator of various phenomena in the universe, such as early dust-like stages at which such objects can be formed, as the first-order phase transitions in which bubble collisions can lead to formation of primordial black holes. Primordial black hole evaporation is a very non-trivial way to have non-equilibrium particles in the universe after primordial nuclear synthesis. And it just is related with the question whether strong non-homogeneities can be present in the universe. And these non-homogeneities may be energy density non-homogeneities and some nonlinear structures, or it may be baryon excess non-homogeneity. And extreme form of such non-homogeneity is antimatter. So actually in phase transitions, they can take place at high temperatures or in inflationary universe, and there may appear topological defects. And simple U1 model, just which is used in axion and axion-like physics, which was discussed before. So let me only draw attention to the following point. If such a first phase transition takes place after reheating, then correlation radius is very small. And so that the closed circle on changing the phase on 2 pi gives you singularity which has geometrical place over line. It is axion string. And axion string network, which disappears after the second phase transition, it gives us these unstable topological defects because after second phase transition, you have a wall surrounded by string structure. It is unstable, but the energy density distribution of the coherent oscillations of axion field, they correlate and they just become a replica of this unstable structure. And it leads to a large scale phenomena which just gives us a very non-trivial effects, and is quite a problem for invisible for axion and axion-like cosmology. So it was also already mentioned, and I think in comprehensive review by Alexander that primordial black holes is something what is maybe explaining what we observe now. And the important point is that in a scenario in which the first phase transition in axion-like models takes place in inflationary phase, it is possible to have closed walls which collapse in black holes, and they are formed in cluster. And the important point here is that their spectrum in this situation is determined by fundamental parameters of the phase transitions of the first phase transition and second phase transition, so that you have the condition that black hole is formed when closed wall just can go within its gravitational radius, and it means that gravitational radius exceeds the width of wall. and it gives you minimal estimation for the mass, and the maximal principal estimation comes from the condition that the wall is not too large, because if it is too large, then it starts to dominate in the local part of the within the horizon before it goes out as a whole, so that the parts which are well dominated, they start to expand superluminally, and we never can observe that. It leads to non-trivial relationship between formation of massive black holes in this closed wall collapse with gravitational wave signal, which is maybe within the reach of the gravitational wave cosmology. And just the important point is that this scenario just also leads to formation of primordial black hole clouds, and this clustering of black holes facilitates formation of binaries. And well, recent result of very massive black hole merger just maybe another argument in favor of both conjecture that observed black holes are primordial. So let me also turn to another possible messenger of physics of baryosynthesis. If baryosynthesis is non-homogeneous, what is not the case in general, but it may in all the mechanisms of baryosynthesis, there are possibilities to have non-homogeneous mechanism in extreme form. It gives you excess not of baryons but antibaryons in some regions. And these regions should be sufficiently large, otherwise surrounding matter should completely annihilate with excess of antimatter. So actually, the minimal mass comes from the condition that the mass within this radius, within this region, is no less than 1,000 solar masses. It may happen in the model of spontaneous baryosynthesis. And then we have the possibility to have antimatter polluting our galaxy, but such pollution, such annihilation just gives you gamma ray background, which corresponds to what Egret observed, but it is not the proof of their existence, because any source of pi zeros gives you the same thing. More serious argument is that it's very hard to create anti-helium in collision of high energy cosmic rays, while here it is the second by the abundance element of antimatter. Anti-helium flux can be a very serious point, and IMS2 started to claim that they do observe some candidates for anti-helium, first anti-helium 3, and they claimed 2 years ago that they have 8 clear single track events with -2 charge and helium mass, and but they need more statistics. However, they even saw something which they cannot call event. They should check very carefully that it is not background, but and we hope that to 2024, the more definite answer about 5 sigma significance will be possible. So let me come to conclusions. Physical basis of modern cosmology implies processes in very early universe which involve new physics. Different dark matter candidates follow from different motivation to extend the standard model and can coexist in multi-component dark matter. New stable and metastable particles, topological defects, evaporating primordial black holes provide probes for physics of very early universe. Here, a strong nonlinear structure can provide multimessenger cosmological probes for physics organization models with baryosynthesis and dark matter. And these properties just correspond to the basic principles of cosmic particle physics, so that we can combine for any new physics scale effects in accelerators, in colliders, astrophysical effects, and cosmological probes. And we have next year an occasion to discuss this question in celebrating 100th anniversary of Sakharov.
5 minutes.
Yes, I'm finished. Thank you. So, by new achievements in studies of physics and cosmology beyond the standard model, I'd like to draw attention that to my session 8, The Universe of Andrei Sakharov, which I plan to arrange in the framework of the first electronic conference on universe. And so you all are welcome to contribute to the program of this session. And it may be a good occasion to have discussions, so let me also make an announcement that you may have seen the logo of Journal of Physics, and we plan to invite people who are interested to contribute a special issue dedicated to the topics of today of our present conference. So thank you, everybody.
Okay. Thank you very much for your interesting talk.